Now, because these waves propagate as a flux and not as a wave, they can't be viewed as waves in a medium. The flux is the medium. This flux exists independently in addition to elementary particles, which is why I call it an elementary waves or an elementary flux.
You're going to lose this audience at 11 o'clock.
Are you all leaving at 11?
No. Some of
Well, maybe I should take a few questions and then stay after 11 for those who do have to leave.
Let's see the Feynman diagrams briefly. These fluxes move the velocity of light?
Yes, they all move with the velocity of light, including the ones for particles that move more slowly. Let me see if I can just quickly do what I have to do first here.
We do have a tour group coming in at 11. So.
Oh, really? Into here?
Yes.
Oh, nice. All right, in that case, I'm just going to have to very rapidly indicate the rest of this. And I'm sorry I took much longer than I thought. Can we go to the next slide? This just shows a simple Feynman diagram for electron-muon scattering. And one of the, imagine a detector over here and having its flux coming in. There'll also be a flux coming in this way that's disorganized, and there'll be a photon flux coming in this way. And at this point, the incoming one will interact with those two and organize part of this one and organize part of that one, which then can also interact with fluxes coming in these two directions and interact at that point. Basically, what this theory says is that instead of these lines representing propagators going in all directions, actually each individual direction with a particular set of vertices represents one of these fluxes. And a propagator then would be fluxes that are coming into this point from all directions, and they would come out in all directions. You can imagine the point organizing all the fluxes from all directions, and then what comes out has a common phase and will look just like a Schrodinger wave. But what's actually going on is actual straight line motion of these fluxes and their interaction at different points. The mathematics looks exactly like Feynman's analysis.
Is the vertex space source
now? Here, it's a point at which this organized flux interacts to organize this one. So now you'll have an organized piece coming out. It'll have the same internal vector as was carried here and a common phase. Actually, it'll be inverted in this case. You get a minus sign, so it'll be phase shifted. So if you have a detector over here emitting this, then you get this diagram and it would scatter towards some source. Now, a particle also is involved here, though. I have to get to that. Let's see. See, I'm leaving out part of this as I go along. These fluxes propagate everywhere in space in all directions all the time. And they're always around, but pieces can be organized by particles. I guess I need to look at the next slide. You have the next slide, please. A particle, when it travels following its flux, will interact with other fluxes in the environment and form patterns exactly like what the particle could do if it were to scatter. A moving electron could absorb a photon and scatter to some new direction. So in the process of following its wave, it acts to organize and therefore appear to emit these organized fluxes. It's not really emitting them. They're actually coming in and just being reorganized when they interact with the particle and then go on out. But it'll look just as if the particle were emitting these fluxes. So if we look at the next slide, a particle as it moves, this is like the particle in the previous slide, it carries around with it these Feynman diagrams in effect, because it emits some secondary fluxes which themselves can then interact further with other fluxes. So you can picture a particle as it moves following its wave as carrying with it the set of all the different Feynman diagrams. And if you have a detector here and it emits a flux that can interact through one of these diagrams and come to a source and stimulate the emission of another particle. That particle follows its flux. Now as it travels, when it gets here, the flux can stimulate the emission of a particle photon, which will travel over to the other particle and scatter it. It goes along here. Another particle photon can be emitted, which will, now this particle will be over here, it will scatter it. This particle will travel on to the detector. So the motion of all the particles will look just like the same diagram. But the beauty of this theory now is, if you imagine all the different Feynman diagrams, they all add together to produce the net flux coming toward the source. All those different amplitudes add. See, it's the intensity here that stimulates the particle. So you see in direct, clear physical terms why you add all the amplitudes and only square the result to get the probability that the particle makes its trip. But when the particle travels, it only has to follow one of the diagrams. It doesn't have to be everywhere at once. It just follows one path. The cross-section, just like in the double slit, is already determined at the source by the intensity of this net flux. So you can picture the wave interactions as picturable, because that's just fluxes interacting as waves. And the same diagrams can picture the particle process, because the particle doesn't have to follow all the diagrams. It only has to follow one of them to get the right answer. This is just like before, where you have many different things the waves might do, but the particle then does one of them.